Hello, and welcome to the second part of the ASBOG 2019 practice exam walkthrough. So this is going to be the remaining 20 questions of the exam that I didn't touch on in the last video. Hopefully I can figure out how to make an annotation or link the other video here. So, if you haven't watched the first part, you can go ahead and take a look at that before you look at this one. In any case, I apologize for the videos being particularly long. I hope you understand that, I want to give every question, the time that it needs to be explained. In any case, let's go ahead and get started and tackle the first one for this video, which is number 21. So which of the following safety factor values for slope stability shows that a slope is considered stable? So this is a geologic engineering problem. Not a lot of undergraduates get exposed to this type of information. Not every university has that as a course. I know my undergrad university did, but it was only offered, every so often, which I never got the chance to take it. But in any case, I do know that safety factors greater than 1 are considered stable, and that's what we are looking for. And safety factors close to 1 are going to be marginally stable, and those slopes are going to be the kind that need some type of attention, either an engineering structure or some analyses to get a sense of what's going on in the area. But since I do know that, let me go ahead and look at the answer choices. So between 0 and 1, between 0 and -1, greater than 1, less than -1. So I know that safety factors greater than 1 are considered stable. So I know, let's see here. I guess I should select a marker. That would be helpful. C is the correct answer. Okay, 22. The effects of solution during diagenesis can be seen in imbricate structures, flute marks, mud interclass, and stylites. So imbricate structures refer to the orientation of class in the same direction. But so in geology, there's always, like 5 definitions for a single word. And this term is no exception. Imbricate structures also refer to nearly parallel and overlapping minor thrust faults or high angle faults. So not dealing with solution. So we're going to go ahead and just cancel this one out. Mark it out, I guess, not cancel, but you get the point. Flute marks. So flute marks, those happen when you have scouring, oh wow, I can't talk today, scouring into fine, soft sediment from really turbulent water flow. So again, not anything to do with solution. So we're just going to mark that out. Mud interclass. So that's interesting. So I think we need to take particular attention, or pay particular attention here to the difference between intra and interclass. So intra means, so interclass is in between the class, and intraclass is in the class. But those are separate things. So what I think this is referring to here is like a mud matrix. Yeah, a fine-grained matrix is what I think this is referring to here. Not entirely sure what's going on here, but Mud interclass solution. We'll keep it on the board for now, but let's go ahead and look at letter D. And if that doesn't make any sense, then we'll come back to see and see what's up there. So stylolites, those are serrated surfaces formed by pressure solution. Oh, okay. So pressure solution, effects of solution, diagenesis, awesome. Looks like, I mean, I feel pretty comfortable not even going back to C. I think D is a good answer choice. Okay, 23. Limestones containing appreciable amounts of clay are represented graphically on a lithologic log by what? So first things first, I'm not even going to look at the answer choices. I know that limestone is generally represented by, like, you know, this blocky arrangement. Please excuse my poor drawing. I'm not an artist, but I think we all know what I'm trying to draw here. So let's look at what we got. Using the standard limestone symbol. Okay, so we wouldn't want to use that. If we have appreciable amounts of clay, that means we're not going to ignore it, right? So we can't just use the regular old limestone symbol. We got to use something else. Modifying the limestone symbol by adding a short dash within each box. So what would that look like? So I'm going to take another color. Let's use green. I don't think I've used green. And we started putting little dashes in the boxes. Okay. So what would that mean? So to me, this means limestone with a fine grain mud. Oh, interesting. But let's go ahead and look at the other options, just so we're 100% confident that B is the correct answer choice. But I'm pretty sure it is, but let's continue. Adding the symbol by adding dots within each box. So let's use red in another box. Let's see what, so if I did that, oops, I guess I shifted it a little bit. So if I did that, what does that tell me? So that to me says a limestone with like some sand, which is not what we have here. So pretty confident that's not it. Modifying the limestone symbol from a rectangle to a, okay, that's just nonsense. We can ignore that. So B is definitely the correct answer. I've never seen a parallelogram in a lithologic log. So maybe that exists, maybe it doesn't. I've never seen it. I'm just going to go with what I know and say that's not important for us. Okay, number 24. You find that in developing a GIS product with several layers of information, there is an apparent conflict between the USGS topographic map completed in the 1975 data layer, 1975, and recently acquired geologic data layer information with GPS locational control. The problem is likely to be what? The ARC info software program is unable to handle mistakes, failure to make adjustments, conflict between scanned and digitized information. So this is probably unlikely. Mistakes in 1975 topographic map, maybe. Again, I'm going to say unlikely. And again, that's likely is the answer we're looking for. C looks very interesting because if you think about it, if this is completed in 1975 and we are not readjusting to the 1983 North American datum, which is going to correct distortions and you know, you would still be able to georeference, but you know, there's still going to be an issue there. And I think the disconnect here, I think this is important. I think the 1975 and the 1983, I think you don't even really need to have a lot of GIS background to answer this question. I think just looking at the dates, you can, you know, make a reasonable assumption that, if you're not you're not making adjustments for the most recent data with this data, then there's going to be a disconnect, and you're going to have some distortions, and who knows what else. So I think C is going to be our best option there. All right, so let's go on and let's look at 25. Okay, an esker. So here is a glacial geology question. I don't know if we've seen, it's been a minute since I did the first half of the video, so I don't remember exactly if we've seen a glacial question yet. But in any case, I'm kind of excited. So an esker, let's go through the options. A, more or less linear ridge formed at the end of a glacial advance. So that sounds to me like a terminal moraine. So terminal moraines are also called end moraines. There's not really enough space. I wish there was, but let's see here. I'll start up here. So terminal or end moraine is going to be A. That's what that is, a streamlined glacial landform. So streamlined landforms refer to erosional features that are produced by continental glaciers. And so that's what this is specifically referring to by saying streamlined. So in this case, the two landforms that come to mind are either a drumlin. So I'm going to run out of room, but drumlin, which is just an elongated hill. I'm not even going to try to attempt to draw it on this page. Or the smaller, which a smaller hill-ish type thing, which is also a glacially streamlined feature, which is called a roche-moutonné. I'll write that over here just because it's a little bit long. Let's see, I think it's spelled like this. Let's see, moutonné. I think there's an accent right there. Maybe there's an extra E. Unclear, but it looks something like that, roche-moutonné. And those roche-moutonnées and drumlins, they usually occur in a very similar environment and are associated with each other. C, a conical hill composed predominantly of sand and gravel. So mound-like hills of ice, so where you have a mound-like hill of ice contact stratified drift, that's a came. And so that's came. And you get those when sediments that are lodged in crevasses either in or on the surface of stagnant ice is deposited when ice melts. So again, so all of these are not eskers. So D better be an esker. A sinuous ridge subparallel to glacial flow composed predominantly of sand and gravel. So I know that an esker, so in my own words, an esker is a long, narrow, kind of sinuous, winding ridge that's formed by deposition from a stream that flows either within or at the base of the ice. And that definition most closely fits D. And so one of the strategies I like to use is putting things into my own words and then trying to find the answer that most closely matches that. And I think that gives you a really high confidence that you've chosen the correct answer, because primarily because you are producing that answer. And I think that kind of removes yourself from answer traps or any other complications that you might run into from trying to select from the answer choices. So sometimes I like to think about questions before I even look at the answer choices, just because I think I end up walking away very confident in my answer. So let's move on to 26. Biostratigraphic zones are employed to establish what? So biostratigraphy, I know that's a correlation method. And so I have to think, what is it based on? So there's things like chronostratigraphy, biostratigraphy, lithostratigraphy. This specifically relies on studying in situ fossil distributions of index fossils. So fossils that are stratigraphically restricted and geographically widespread. And we use those to correlate successions. So knowing that, let's go ahead and look at the answers, which is continuity of formations, age equivalent within sedimentary sequences, absolute ages of successive formations, sedimentary provenance, active during deposition. Okay, so continuity formations. Reasoning through this one, just because you have a fossil over here and a fossil over here and they're both the same does not mean that there's some laterally continuous unit, especially if it's like really widespread. That doesn't necessarily indicate that. So not used for continuity of formation. Age equivalence within sedimentary sequences. So what I'm thinking with this is, we can say, oh, this is from the Ordovician. So this is, I don't know, this is green. And so, oh, this is also green. This is also Ordovician in age. And so we can tell that these units are equivalent in age because of the fossils that they have in them. And so that seems like a pretty good answer choice, but let's go ahead and knock out the last two just to make sure. Absolute ages of successive formations. So absolute ages are referring to a very specific numerical age of a material. So generally that's using like radiometric dating, and that's not what we're using here. We're using fossils to make our age equivalencies. Sedimentary provenance. So provenance is just the source region. Source region of a sediment sample. And that's, your fossils are not going to tell you that specifically. So we can go ahead and remove that one, but let's just go ahead and move on and say that B is the correct answer. Very confident that it is. 27, what liquid limit and plasticity index values would be associated with a soil classified CH? All right, so these are called, let's see if I can spell this correctly, Atterberg limits. I think that's how you spell that. And these are all, this is also a geologic engineering concept. You might cover this in a geomorph class depending on your professor, but in any case, the secret to this that I like to remember is that so you see this H here, this can also be replaced with an L. So you can have CH and you can have CL. And those are different types of soils. But what I remember is that this soil with an H has a liquid limit that is greater than 50. And I remember that the CL, the one with the L symbol, has a liquid limit less than 50. And I remember that because L less than, and then I just worked my way through. And then knowing that, I remember that a CL soil has low plasticity. So I'm going to say low P to save room. And a CH is going to have high plasticity. So I'm going to say high P. So knowing that, so we have a CH soil, so we're going to have a liquid limit that is greater than 50. So automatically, let's see what we can do. If we know it's not A because liquid limit of 12. Could be B, could be C, and could not be D. All right, so we have a 50-50 chance. If we just remembered the H and L lower and or higher and lower than 50, you'd have a 50-50 shot. But I did remember the high plasticity and low plasticity, and I think high plasticity means like greater than like 17 or 15 or something, and low is less than that. So looking at our answer options, we have B, plasticity greater than 38, and 11. So since we have the one that has the higher plasticity, we know B is our correct answer. All right. Moving on to 28. Lithostratigraphic sequences can be used to interpret what? So geologic history, isolated outcrops, earthquake probability, absolute ages. So we already talked about absolute ages and how that's, usually reserved for radiometric dating. And so we can go ahead and mark off that because lithostratigraphic sequences are units that are correlated based on things like petrology, geochemistry, mineralogy, lateral variation. So D's wrong. Let's see what else we got here. The unit sequences are not going to tell you anything about earthquake probability. And they're not going to tell you anything about isolated outcrops either. So A is our only remaining answer choice, which is geologic history, which does make a lot of sense considering what these units are correlated on. They're correlated based on, are they unconformable? Are they laterally continuous? So things like that. So that can give you a really, can help you dissect the history of, specific sequences. And so pretty confident about that one. All right, I'm going to go ahead and just move up a little bit for 29. Which of the following anions is the least reactive and most persistent tracer of a geochemical contaminant plume? Carbonate, bicarbonate, okay. So what is this question really asking me? Do I need to know how to trace a contaminant plume? Like, this is the fundamentals of geology exam. This is not the PG exam. You're not expected to apply geology, this is not a question of you applying geology professionally in the field. This is a question about basics, about introductory material that you learned throughout your undergraduate career. And so we have to keep that in mind. So this question probably is a little bit more simple than we're being led to believe. And so when it's talking about least reactive and persistent tracers, or anions, in this case, it's referring to what are called conservative ions. And conservative ions, they fully dissociate from their conjugate acids and bases over the normal range of pH that you would see in natural water. And they come from high solubility salts. And they're things like, let's see here, sodium, potassium, calcium's one, magnesium also, chlorine, that's enough. And so those are generally the ones that we use for studies, especially just because they are least reactive and they're pretty persistent. On the offhand, so I know we're not being asked for non-conservative ions, but just for the sake of explanation and clarity, we'll discuss those here for a sec. So non-conservative ones, those are things like bicarbonate, carbonate, that's a 2. Any of the phosphate species, so like the conjugate bases of so virtually all non-conservative species are anions, but we have, the really main 2 exceptions are hydrogen. All right. So enough of that. Let's go ahead and try to answer the question. So which of the following is least reactive and most resistant? So I guess I should, I'll do it in red just so we can see conservative and non, just so we can kind of differentiate those. So so we know that carbonate is not conservative. So this is not going to be least reactive and most persistent. Bicarbonate either. Chlorine. Not chlorine. Well, I'm tired. Yes. So let's see. And then those phosphate species. So boom. Looks like we are left with C as our final answer. And that's true. That's pretty common. So we can be pretty confident about that. All right. Moving on to 30. The grain size distribution curve illustrated here indicates that the sand is what? Poorly sorted, poorly graded, uniformly sorted, well sorted. So we're using sorted and graded, and those are opposites. Geologists tend to use sorting, while engineers tend to say things are graded. But geologists, whether we like it or not, we also have to know what it means to be poorly graded or well graded. But just, for a quick review, sorting refers to the distribution of grain sizes of a sediment. So something that's well graded, because they're opposites, graded and sorted, they're opposites. So if something that's well graded, so I'll say WG, well graded, that's a poor G, whatever, means that we have a good distribution of particles. You're going to see a lot of sizes represented, and this is equivalent to poorly sorted. All right, and I know that something that's poorly graded, that's going to be a not. You're not going to have a good distribution. And so that is the equivalent of well sorted. And so that means you're going to have similar sizes. And so on a grain size distribution curve, what we would see for something that's well sorted is that your curve would look something like this, in that you would have a very specific range. Looks like a very crappy integral symbol, but a very specific range, a very small range, where your sizes are coming from. And so they're all going to be pretty similar. Where if something is poorly sorted, you're going to have something that looks, okay, well, that's really bad. But let's see here. I'll do it again. Maybe that's better. Where you're going to have a lot wider range of sizes represented in your sample. So what we have here looks a lot more like this than it does this. And so let's walk through the answer choices. I know this may be a little confusing for people because these are opposites, but hopefully they don't do anything too tricky. So poorly sorted. So poorly sorted is well graded. And I guess for labeling purposes, I guess I should say this is well sorted and this is poorly sorted. This is all over the place, but hopefully it makes sense. So hopefully this will help. Let's see here. So poorly sorted, it would look like this. Okay, that seems reasonable enough, but let's go ahead and just, walk through it. Poorly graded. So if it was poorly graded, it would be well sorted and it would look like this. So nope. Uniformly sorted, nope. If it was well sorted, so let's see, well sorted is also poorly graded. So it looks like they gave us equivalent statements, but they seem worlds apart. But we're smarter than that, so we know that those are the same thing. So we are extremely confident. A, poorly sorted. All right, awesome. Let's go ahead and look on kind of to 31. So 31. If the beds are vertical in figure 29, what type of fault does it represent? So that's saying that these beds are coming out of the screen and into the screen, and we are looking at them on plan view. So we're looking down on them. So what I like to do, even with intro geology students and even people who are taking the ASBOG, is I like to draw a little stick figure. And it seems a little elementary, but it gets the point across and it works. So here's my little stick figure. If I look across the fault, what type of relative motion am I seeing? So if I'm looking across, I'm seeing that the other side is moving to the left. And if I stand on this side, what kind of movement do I see? I see that this side is also moving to the left. All right, so what does that mean in terms of the answer choices? So it's thrust fault. So thrust fault, that's a high angle fault. We're having thrusting of units. That's not happening here. So it's reverse fault. So that's where we have, one fault moving, yeah, nope, that's not. A right lateral fault, so that means that the relative motion would be to the right. Well, that's not the case here. We are moving to the left, regardless of which side we're on. So we know that one's not the answer. So D, left lateral fault, is our correct answer. Cool. Okay, 32. What is the approximate total volume, volume is generally pretty straightforward, of limestone, which can be quarried from the property shown in figure 83 if mining extends to a depth of 350 feet. Okay, so let me zoom in. What does this say? 500 feet, 1,000 feet, and a depth of 350. Okay, so I'm gonna start my math up here and hopefully I have enough room. But if we have 500 feet and we have times 1,000 feet, and then we're given 350 feet. So we're given 3 dimensions, which is a good sign since we're asked to find a volume. I'll just break this down. So that's 500,000 square feet. I guess that's important here. Times 350 feet. I'll have to put that in my calculator. All right, so that's equal to 175 million cubic feet. Okay, well, problem that we've run into is that none of our answer choices are in cubic feet. But that's not a problem for me. I remember a neat little conversion that will help me out here. So I remember that 1 cubic yard, which is what all these answer choices are in, is equal to 27 cubic feet. So all I have to do is just divide this by 27. What does that get me? So that gets me 6,481,481 cubic yards. And so the close answer to that, we are looking for approximate, so that's fine, is C. All right, that wasn't too difficult. So this was kind of, I'm not sure exactly what category this would fall into, but in any case, it wasn't really requiring any hyper specific knowledge. It was just, you know, I guess the most difficult part was remembering this conversion. So maybe that's what they're testing here. All right, let's move on to 33. 33, if the net volume of precipitation entering a drainage basin exceeds the surface water volume coming out with no change in surface storage, then water is recharging the groundwater system, water is discharging, evapotranspiration rates have decreased, groundwater storage remains constant because of loss of water to evapotranspiration. So let's define a few things here. I think that's important. Recharge. So recharge is just the addition of water to the water table as the result of infiltration of rain, snowmelt, things like that. Where discharge is kind of the opposite, where we have movement of groundwater from the subsurface to the surface. And then groundwater storage is basically what it sounds like. It's the amount of groundwater that's in an aquifer or some type of drainage basin. And so when I was reading this question, the equation that came to mind from hydrogeology was recharge minus discharge equals the change in storage. And so that, in essence, it makes this the input, and this is the output. All right. And I know that in a long-term undisturbed system, recharge minus discharge is going to be approximately 0. So that's just kind of the background I'm working with here. Net volume of precipitation entering a drainage basin exceeds the surface water coming out. So what that says to me, I'll do this in a different color. What that says to me is that we have input is greater than our output. So let's start tackling the questions. Water is recharging the groundwater system. If input is greater than output, it most certainly is recharging the groundwater system. But maybe there's a better answer. Water is discharging from the groundwater system. You're not having any change in surface storage. So no. Evapotranspiration rates have decreased, remains constant because of okay, neither of these are great. A is the most reasonable answer here, because we are most certainly beyond a doubt recharging the system because we have input that is much greater than the output and we're not seeing a change in the surface storage. So, okay. 34. Which of the following is not, that's important, not commonly a natural constituent of groundwater? So what I want to do then is think about where each one of these things comes from and identify the one that's not natural. So iron in groundwater is the direct result of the natural existence of just underground rock formations and the interaction of water-rock interactions. Carbonate generally comes from carbon dioxide and water interacting with limestone. Again, both of these are very natural processes, naturally occurring. So chloride. So chloride, interesting case here because chloride has both a natural and an anthropogenic source. So you see chlorides as a result of like road de-icing salts from septic tank effluents, landfill leachates, things of that nature. But you also see chlorides because of like saltwater aquifers, sea spray, coastal flooding. All of those are natural ways for chloride to get into fresh water. So could argue either point, but let's move on to D. D is going to be much more interesting. So D, nitrates. A high concentration of nitrates is a problem, particularly in areas that are high or have a lot of agriculture, just because the nitrates come from fertilizer runoff, and these are a particular problem. So D is the correct answer. Oops. Got carried away. An uplifted block bounded by normal faults is known as an atoll, geo, graben, horst. Okay, so first things first, I recognize some of these terms and I recognize that they do not go with what we're talking about. So a geo is a seamount, not a normal fault. An atoll is a ring-shaped coral reef that generally forms around lagoons. So A and B out of here. So we're left with horst and graben. You usually hear those terms when we're talking about horst and graben topography. So let's see how my drawing on with this pen turns out. So I'll use two different colors to help illustrate my point here. Oh, that's not going to turn out well. Oh well, we're going to go with it. So, yeah, that didn't work out like I wanted it to. Where is my eraser? Does this program have an eraser? Maybe I'll just, wow, okay. So we're just gonna delete and start over. So what I'm trying to do is draw horst and graben topography. So there's that. I want to draw this, and I want to draw this. This will work now. Cool. So what we have here, I'll label it in black. So this block is called the horst. And this right here is called the graben. And in a normal fault, the horst is going up and the graben is going down. And in a reverse fault, the opposite is true. So an uplifted block bounded by normal faults, in this case, is D, horst. Okay, 36. Your client calls you to sample a series of monitor wells that they installed on their property. Your review of the geologic setting determines that the wells are located such that no contamination could be detected. You should notify the board, refuse the job, inform the client, sample the wells. So you have a responsibility to your client, and if the wells have been installed in such a way that no contamination could be detected, but so that leaves up the possibility that there is contamination that's not being detected. So you need to let the client know. Yeah, so in this case, your responsibility is to the client. You need to make them aware that, the wells are not are not either installed properly, or at least not, deep enough, or, what have you. But for this question, your responsibility is to the client. All right. So it looks like we're getting to the big section. So I'm not going to read this out loud to y'all. I think y'all can read along with me. Okay. So I have a series of questions that are going to be asked based on what I'm going to read and this map down here looks like. All right, so a lot of this information does not seem pertinent, but really my goal of skimming this paragraph was not to retain all the information, but just to know what's there. So if I do need some of it, I can go back and find it and have it, know that it's going to be found there. So, okay, so here's the map, and then give some descriptions of the units. Since this is a timed exam, I'm not going to spend too much time looking at the map right now. We're going to dive straight into the questions, and I'm sure it will require me to look at the map. So what is the correct stratigraphic column for the Corner Bay area? Oldest on bottom and youngest on top. All right, let's get to work. So let's start reading. Beeswax sandstone, Mississippi. Okay, so if they've given some ages already. So if they've given me some ages, I'm going to put these together like a puzzle. No need to reinvent the wheel. What I'm going to do, I'm just going to write out my geologic time scale over here on the side. Okay, so unit B is Mississippian. So I know I can place it here. And a holiday formation is Miocene. So Miocene is in the Neogene. So I can place H way up here. So I'm just going to mark these off as I've taken care of them, just so I don't spend time looking at them again. Midway formation is poorly sorted, angular to rounded, coarse defined, coarse sandstone, moderately well cemented, contact with unit P above. Okay, so it tells me it's in contact with unit P above it. All right. So let's go ahead and read P. So okay, so they give me an age for P. Okay, so they say that's Jurassic. So okay, cool. So I can work with that. So P is here, and I'll mark that off. And this is the P above. So I know that, I don't know for certain that M is Triassic, but this is just the space I have. So I'm going to say M is there because it says it's P is above. Running Ridges limestone has preserved fossils at the top. Okay. So it looks like we have dipping, opposite directions there. Some erosion going on over here. So that's interesting. Let's keep going. Singing Sands, well sorted. So where's that? Singing Sands. S is up here in this bay. Okay, so this is the youngest. So it's S, way up here. I'll mark that off. And then X-ray granite, coarse crystalline white, probably Precambrian, zebra complex, weathers into complex. Okay, so in order for this type of regular topography to have occurred, Z must be older than X. So I'll just, Z, X. And it leaves R and D. So I'm not going to waste time trying to put those anywhere. I'm going to see what our answer choices are. So, oops, I didn't mean to do that. But so this one says X is the youngest, so that's wrong. This says S is the youngest. Okay, I believe that. This says S is the youngest. Okay, so I know it's not D either. So 50-50 shot. SH, PM, SH, PM. Okay, so they place PM close together on both of these, so that's not helpful. They place R in both places, so I guess R goes there. B. They both place B there, and they both place D, as in dog, there, so that apparently didn't matter. Okay, so the difference between these two is whether Z and X are older. Well, I said because of the irregular topography that Z had to be older, so C, as in cat, is our correct answer. Cool, that was fun. Deep exploration holes drilled at the quarry in the X-ray granite, which is X, intersected the Running Ridges limestone unit R. Based on this drill hole data, what is the best interpretation of this contact? So we had R and X. Okay, interesting. Normal fault. So we talked about a normal fault earlier, where we have the footwall that's going up. Ooh, wow, that very bad. So where we have the footwall going up and the hanging wall going down, that's not going to, usually when we see, older and younger units close together, that's generally because they've been thrusted, on top of each other. But normal fault, that's just, relative movement. Thrust fault. That one's looking very promising. Dextral fault, so that's just a right lateral strike slip. Sinistral, that's a left lateral. And we're not going to see really old and really young material together in any of these except a thrust fault. Booyah. The contact between the holiday formation, which is H, and beeswax, which is B. So H and B, let's go back and look. So H is all of this gray material. It's, let's see, interbedded fluvial and tidal flat sands, silts and muds. Okay. Where B is angular quartz sandstones, very well cemented. So I mentioned earlier there was some erosion going on here. So that's interesting. So let's take a look at our answer choices. So we have a fault contact. No fault there. Intrusive contact, neither of these are intrusive. Normal stratigraphic, no, it's not normal. We see some erosion or you know, an area of non-deposition maybe. But I'm gonna go with erosion. That seems most probable. Angular unconformity. Aha. That's the one we're looking for. And that makes sense, right? Like, you know, these are angular, there's erosion. Yeah, that fits what we're looking for. All right, the last question. The quarry located in the X-ray granite is a dimension stone quarry. This suggests that the X-ray granite is what? So dimension stone is rock that's quarried for very specific purposes and very specific characteristics, dimensions, things like that. So things like granite, limestone, alabaster, I think, is one of those. Usually you want to polish those types of rocks. And so hardness is important and you don't want them to crack. So like granite countertops is really, you know, famous. Massive and unfractured, highly fractured, deeply weathered, closely spaced joints. So like I said, we usually want to polish these types of we want to polish dimension stone. It's quarried for a very particular specific reason because of the certain characteristics it has, its mineralogy, its hardness, things like that. And so, you know, if it's fractured, you know, it's going to be easily broken. So massive and unfractured is the most reasonable answer. All right. Well, I think that wraps up everything. We've gone over every question. So as you're probably aware, the ASBOG exam is actually 140 questions, so you'd have 100 more to go. Hopefully this has been helpful. I appreciate the feedback I've gotten. Just like with the first part of this walkthrough, if I notice, you know, I'll go through and watch this again, and if I notice any errors, or if anyone brings them to my attention, I'll put them in the description with a timestamp. But hopefully I didn't mess up too badly, other than calling chloride chlorine a couple times there, but that's okay. Everyone makes mistakes. But in any case, I hope you've enjoyed. Give me a thumbs up if you've enjoyed watching, and hopefully this will help you in your preparation for the upcoming ASBOG exam. In any case, until next time, thanks guys.